Do 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 do. Do 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 do. Do 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 do. Do 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 do. Welcome to today's video. We're going to talk about two different things in this video. We're going to first talk about multiplication of vectors, so what the difference is between cross product and dot product. You can see that on the screen there now. And we're also going to take a look at the idea of work. And I know that's a foreign concept to some of you since you're teenagers, but we're going to delve into what the idea of work is in a physics setting and how multiplication of vectors and work are related. So let's jump right in with multiplication of vectors. So when we multiply vectors, we can do it one of two ways. So the first way, and what you would probably be most familiar with, would be the cross product. So if I have two vectors, A times B, and we call this the cross product when we put an X here. When you multiply two vectors together, you would expect to get some other vector, vector C. So when you find the cross product, you find another vector. So we'll just write here, the result is another vector. Okay, so that's what you would think of as regular multiplication probably. The dot product. So we have vector A again. But when we say the dot product, we put a dot here and then B. So in a math setting, this and this mean the exact same thing. They both mean multiply. Here with vectors, they also mean multiply, but we multiply in a different way. When you find the dot product of A and B, you still get C, but the difference is this is not a vector. This is a scalar. So the result is a scalar. And no, that doesn't just mean that we're going to forget about the direction and do the exact same thing. Dot product is a little bit different. So what dot product actually does, so let's write in here, dot product finds the size, and when we say size, we're talking about a scalar of the product. So far sounds the same, right? The size of the the size of the product. Let's make sure I spell correctly. So dot product finds the size of the product of two vectors. Here's the key part, in the same direction. This is the part that makes this different than the cross product. So what does that mean? Let's take a look at an example here and actually write down how we find the dot product. So if I have two vectors, let's say vector A and vector B, A and B. The dot product, if I wanted to know what A dot B is, I'm asked to find what is the product of these two in the same direction. Well, you can see they're not pointed in the same direction right now. So how do we actually do that? Well, we have to take the component of A that's going in the same direction as B. And we would actually call this A sub B. We could use that notation. So this is the component of A, just like we've been doing before, breaking up our forces into their x and y components. We can break up this other vector into a component that's going the same direction as B. The angle between them here we would just call theta. It could be anything right now. That looks like I've drawn probably about a 30-degree angle, maybe a 40-degree angle. So let's see, how do I actually calculate what AB is? Well, if here's theta, this would be, let's use a different color. Here is your 90, so this would be the hypotenuse, this would be the opposite, this would be the adjacent. So adjacent and hypotenuse is cosine. So cosine of theta equals adjacent over hypotenuse. So we have cosine theta. The adjacent side was that A sub B. and the hypotenuse is just A. And we're going to do one other thing here. I'm going to put these lines around it. What that means is absolute value. All absolute value is just don't use a sign. So if it was negative, just forget about the negative, which you guys are really good at doing anyway. So we just treat everything as being positive. If I want to know what a sub b is here, I just rearrange. So I'm going to multiply these two together. So a sub b is equal to a times cosine of theta, which is what we've been doing before. So if putting this all together, if I want the dot product of A and B, so A dot B, what do I need? Well, it's in the same direction, so it's AB times B. So we have A sub B times B. And again, we're just using absolute value here, so forgetting about our signs. We can simplify. A sub B we just saw was A cos theta, so A cos theta times B. And usually when we write it, we put the cos theta at the end, so we would have A times B times cosine of theta. So the dot product of two vectors is just multiplying their values together and then multiplying by the cosine of the angle in between them. Okay, so keep this in mind. Dot product is not the same as cross product. We are unsurprisingly going to do something with dot product here in a second. So A dot B is equal to AB cos theta. All right, moving on to work. So again, I told you this might be a foreign concept for some of you. Let's talk about it in terms of physics. What is work in a physics context? So work is just the transfer of energy from one location to another, or, whoops, not of, or one form, whoops, to another. No, that's not your eyes playing tricks on you. That did turn black for a second. So work is just moving something, so transferring energy or from one place to another, or changing it from one form of energy into another. So that's all work is. So in order for something to actually be considered work, we have three requirements. So three requirements. Just like you couldn't tell your parents, oh yeah, I did a ton of work if you just sat on the couch. That is a requirement that you actually can say I did work if you did something. So if you just sat on the couch, you wouldn't have, even in the physics idea of it, you wouldn't have changed location, so no work happened. So in terms of very strictly physics, what are the requirements for something to be considered work? Well, number one, you need a force. So a force needs to be acting on something. Number two, you need a displacement. So you need a way of moving something, and you need it to actually move. And thirdly, the force must be parallel to the displacement. All right. So, with those three in mind, and with our last slide also in mind, it should come as no surprise that work is a dot product. So we're going to go ahead and use this idea of dot product to talk about work. So here's my formula for work. So work, represented by a W, is equal to, number one, our requirement was we need a force, so here's our force. it's a dot product, and the other thing we needed was a displacement. So here's our displacement. So work is the dot product of force and displacement. Nice and easy. And if we talk about this being the dot product, then we can also rewrite this as, remember the dot product, they need to be going in the same direction. So we could rewrite this as the absolute value of the force times the absolute value of the displacement times cosine of the angle in between those two. And sometimes you'll also see this written as work equals force parallel to D. So this part here means the component of the force parallel to D. And notice the notation here. This is dot product. Here I didn't put a dot because that wouldn't make sense if these are already parallel to each other. It wouldn't be necessary. So how do we find the parallel component? We would do F times the cosine of theta and then times D, which is right here. So these are all just rearrangements of the same thing. The one we are going to use the most is right here. This part right here. I don't know how to use a highlighter on here. This is the part that we'll be using the most. Okay, so let's do an example here and see how we do this work calculation. So how much work does it take to push a 20 kilogram box at a constant velocity across a horizontal surface a distance of 100 meters if mu equals 0.50? So we get a lot of information here. Let's draw a picture. So we've got a horizontal surface, we've got a box on top of it with a mass of 20 kilograms. So what all forces do we have? Well, we've got the force of gravity, Fg. We've got the normal force. Those are going to be equal to each other because we have no other vertical forces. We are pushing on a box, so we're going to be pushing it, let's say, to the right. So you've seen me draw an arrow like this. You can also draw it over here as well. Doesn't really matter. So here's our force. And we're told that mu is 0.50, so we know there's friction. So friction. And if it says it's being pushed at a constant velocity, we should realize that that means it's not accelerating, so the net forces in the x direction has to be 0. So what does that tell me? That this force and friction need to be equal to each other. Okay, so if we want to know what the question is asking us, what work is done, then we need F dot D, the dot product of the force times the displacement. So I guess I should have added on here, if the force is applied in this direction, then that means the displacement is going that way as well. So we'll just write it on here. This is also the direction of displacement. Okay, so we need the dot product of force times displacement. That would mean we need absolute value of the force times the absolute value of the displacement times cosine of the angle in between those. So do I know the force? No. What do I know though? It's equivalent to friction. So I know that F is equal to friction, which is equal to mu times n, the fun formula. I know mu. Do I know n yet? No. But what do I know? I know that n is equal to Fg. So I could rewrite this as mu times mg. And in fact, I do know all this stuff now. So what are those values? So 0.50 times the mass of 20 times the acceleration due to gravity, 9.81. So when I punch all those in, what do I get? 0.5 times 0.2 times 9.81. Oh wait, sorry. 0.5 times 20 times 9.81. I should have been able to do that in my head. We get 98.1 newtons. So there is my force of friction, or sorry, my applied force, so 98.1 newtons. Now let's fill stuff in here. So absolute value of 98.1, so just 98.1. Just forget about the fact that it has direction at the moment here. So 98.1 times the displacement. The question says it moves a distance of 100 meters, so 100 times cosine of the angle between them. Well, this one's easy and kind of trivial. So the displacement is to the right along this horizontal surface. The force is also pointed to the right. It didn't tell me it was at an angle or anything. So what is the angle between those? It's just 0. And what is, so let's simplify here. 98.1 times 100 is 9,810. And cosine of 0 is 1. So when we multiply those together, we get 9,810. And what were my units here? So this was a Newton. This is a meter, so Newton meters. And if I round to significant digits, no, let's not bother with that right now. So 9810 Newton meters. That is a unit of work. We also more commonly give a unit of J for joules. So I didn't write that on the last slide. Perhaps we should. I'll just write it at the bottom here. The unit of work is the joule, Joule, and it's written as a J. And 1 joule is equal to 1 Newton meter. Okay, so in this case, this part was kind of trivial, the dot product, the fact that cosine of 0 is 1. But if this had been an angle, an applied force at an angle, something like this, then if this was FA, then you would have had to find FA sub X, probably we would call that. And then it would be this times the displacement times whatever this angle would happen to be. So you'd have to be careful about that. That would have also affected our other calculations, because this would also have a y component, which would affect our normal force calculation and so on and so forth. But in the context of work, that would have given us a different value over here, a value less than 1. So with this in mind, I would like you guys to try questions 1, 2, and 3 on the work, energy, and power worksheet.